Hey, welcome you all for the next lesson on this electromagnetic wave properties and propagation, etc. Let's recap what we learned in our previous lesson. We learned that the electromagnetic wave radiation is produced when an alternating current is applied on an aerial, and it has got two components. One is the vertical component is or the electrical component, and the magnetic component. We also learnt that they travel at 90 degrees to each other generally, and they travel at a constant velocity of 3 into 10 to the power 8 meters per second. Well, not exactly, but for our at this stage of study, we can assume that it is constant at 3 into 10 to the power 8 meters per second. So, in this lesson, what we are going to do, we are going to learn further on some propagation and its properties of propagation in the atmosphere. Let's get on to some more properties. If uninfluenced, the radio waves travel in a straight line. In a given medium, radio waves travel at constant speed. This is important. Uh, constant speed direction also I will add, which is what is coming up. When passing from one medium to another at different refractive index, the velocity of the waves changes. This is important for us to understand. The waves are also deflected towards the medium of higher refractive index. That means they change in their direction as well. So, the radio waves are reflected by objects commensurate with their wavelengths. This is also important. If the wavelength of the wave is 3 centimeters, any particle which is as small as 3 centimeters will try to reflect that particular wave. That's what it means. We all know that shape of the earth is a sphere, and this means that the horizon curves away from the distance of the transmission point, that is where the aerial is located. And if the waves were to travel in straight lines, then it will just have a distance of as given by this formula 1.05 into under root of height, where distance is in nautical mile and height is in terms of feet. So if we were to calculate, let's say at about 10, if an aerial were to transmit a radio wave at 10,000 feet, under root of 10,000 will be 100, 1.05. The range would be just about 105 nautical miles. Is it of any utility? Not at all. 100 nautical miles, hardly any distance. But fortunately, we will soon see other modes of radio wave propagation by which it is able to reach larger distances and being able to be utilized for several other useful applications. We learned that EM waves travel in a straight line, and we try to learn that not necessary. There could be differences or deviations from that rule, which we are going to see. There are two basic properties by which it will change its direction, that is diffraction and scattering. These are the two properties which we are going to learn learn. Now, as you can see, there is an aerial and there is a transmission which is going on, and there is an object at a distance. And normally speaking, that straight lines would have been the straight line uh, travel of the EM waves take place in all different directions, and when it strikes that particular body object, it would have cut off the rest of the things. But because of scattering, these EM waves tend to bend around the bodies, which is what I have shown in this black color. Normal EM waves I have shown as transmitted is shown in blue color, and when it strikes the body, it bends, it turns its direction, and that is what I have shown in a black color. Now, this diffraction scattering, is it uniform? No. How does it vary? It varies as per the frequency. That amount of diffraction is inversely proportional to the frequency. That means lower the frequency, higher is the diffraction, higher is the bending, higher is the change in direction. That means the lower frequency ranges are able to change its direction much more easily. As you go up in the higher frequency range, that is very high frequency and ultra high frequency, there's hardly any change in direction. That's what here it means. Here we will come across a very interesting phenomena called attenuation. What is attenuation? It is loss of energy of the EM wave as it strikes on a particular body. So how does it affect the range and range, etc.? That's what we are going to see here. In this picture, I have shown a reasonably low frequency range. That means the wavelength is a little bit higher, and it travels as shown. Now, when that portion of the wave, when it strikes the earth, what happens? There is attenuation taking place. Attenuation, loss of energy of the wave takes place. That means that portion of the wave tends to slow down. So when that portion of the wave tends to slow down, the upper portion of the waves travel at its constant speed. Therefore, there is a natural tilt which is getting induced. There is a natural tilt which is getting induced for the wave. Now, this, whenever it strikes, when the next wave strikes, it again attenuates and slows down further and further. This carries on over different cycles. This eventually gives rise to a reasonably longer distance of transmissions. Now, how the property of propagation is further affected? What are the other factors? We will see. The type of surface. Different surfaces, different types of surfaces have different conductivities. A desert could be different. A forest thick could be different. Populated areas could be different. And over the sea, this could be different. So that's what we mean by different surfaces have different conductivities. For a given transmission power, a radio wave will travel a longer distance over sea than over dry soil. Because the attenuation, loss of energy in an EM wave is a little bit less when striking over water. And of course, the frequency in use also matters. Higher the frequency is, the greater the attenuation. So we already saw at lower frequency ranges, it's able to travel much longer distance. So one of the reasons is attenuation itself is much higher for higher frequencies. And of course, polarization. In the last lesson, I briefly touched upon the concept of polarization. The plane in which the electrical component travels is called the plane of polarization, and vertically polarized waves are normally used for minimum attenuation. That means the um, electrical component of the wave is transmitted at the vertical plane. Is it suitable for all kinds? That we will see as and when we come across different equipment and utilities, then we will see what kind of polarization is suitable for which kind of transmissions. Um, Maybe by now, maybe you got an idea that frequencies at lower ranges are more suitable for longer ranges. However, it may not be practical. Let's go through further. VHF and above are used only for line of sight communications, and low frequency ranges are suitable for long range. Therefore, uh, uh, VHF or used for communication, VHF, UHF or communication, their ranges are that to that extent restricted. Now, what are the disadvantages of lower frequency? The aerial. Now, you will appreciate that because of the lower frequency, the wavelengths are higher. And we also learned that the aerial size has to be coherent with the size of the wavelength. It has to be in harmony of the wavelength. That is either half, one fourth, etc., etc. And long wavelengths demand longer aerial size. And of course, it picks static noise or long distance travel. And of course, the cost of installation is high. So, its utility is not much. It is getting slowly limited because of its disadvantages. Okay, let's proceed further. We will talk about those waves which travel in the sky. That is the sky waves. Now, the radiation of the sun has considerable effects over the property of atmosphere. That's what we learned, right? That means that in a diffused atmospheric status which is existing at a higher level, when the sun activity is higher, the electrons are set free from their atoms and they exist as loose atoms. So the density of electrons depending on the intensity of the sun rays and the angle at which the sun rays penetrate. Obviously, by midday, it is penetrating at almost perpendicular direction, and so the ionization or the density of the electrons is going to be much higher. The density of electrons results in different identifiable layers of atmosphere with different refractive indices. So that's what I want you all to understand. During, especially when the sun activity is high, different layers of atmosphere take the different levels of ionization is produced. So the the electron density keeps varying almost throughout the entire the layer. And it affects the density of the medium. Now, as we learned that the travel direction and speed of the EM waves will depending on the density of the medium, which is going to have considerable effect. That's what we are going to learn further. As I told you, the electron activity is considerably varied across the atmospheric layers, and here is what is a brief explanation as to electron density, etc. I'm not going to go into the details. I would just expect you to spend about 10 to 15 seconds and learn this in your theory. There is no point just trying to explain what is just about a fact. But I want you to notice that at different distances of the atmosphere, different electron densities are produced, and a little bit of variation properties also I have tried to indicate in this particular slide. I will spend some more time, and I want you all to see this and learn it in your theory. Here, all I have tried to show is that the atmospheric density keeps varying, and EM wave which has left the aerial, if it were to follow a straight line of sight path, it will follow the dotted line. Whereas, because of the change in density of the atmosphere, at every layer it bends and it forms almost like a curved path because of the different refractive index of the atmosphere. Well, actually, in actual atmosphere, it's not a layer by layer separation. It's a gradual change. So the waves also bend gradually. For theoretical purpose, we have shown that it's different layers, different densities, and at every density that the EM waves change its direction. Just for academic purposes, but otherwise, let's understand that it is the rate of the change is gradual and uniform. Further explanation here in this diagram. First, there is a transmitter, and just to make this more clear, first in this I have shown this yellow EM wave. The path of the yellow EM wave, it travels at a particular direction, and gradually it turns, and towards the upper atmosphere it is bending and leaving the atmosphere and escaping into the space. Okay, now study the next wave, which is green in color. Again, it is bending at different levels of atmosphere. It is bending, and at some point it is able to bend fully and return back to the atmosphere. So it is able to reach a farther distance. Similarly, the third black wave. Now, let's see what actually happens. So, let's start with this wave named A, which is normal to the aerial, which is absolutely normal. That means straight vertical to the aerial, and so it will surely escape. And B will also, it's not at a particular convenient angle, and so that also escapes uh, into the atmosphere. And the third wave called C, and thereafter D, it's able to bend fully and return back to the Earth. So, and thereby giving us longer ranges. Let's go through some very important definitions as far as the EM wave propagation is concerned. Firstly, we learned that the ground wave is travels on line of sight principle, and we also learned that it distances achieved are 1.05 into under root of height of transmission, and that's not much. So beyond that, there is no reception of the ground wave. Now let us take the space wave. We learned that space waves at some point it gets reflected, totally internal reflected, and then it part of it reaches back the earth, and this distance over which it has traveled in the process is called the skip distance. Now you will appreciate that there is a space in between this last ground wave and the first space wave, in which no radio transmission was receivable. So this space is called the dead space. Okay, now this a wave which leaves the aerial at normal vertical plane uh, is totally escapes into the atmosphere, and as the angle of transmission keeps gradually increasing, at some point we learned that it starts getting reflected internally. This angle at which the first space wave starts getting internally reflected is called the critical angle. Okay, let's see some factors affecting the propagation and things like that. Firstly, the diurnal effect. That means during the day, the sun activity is high, and therefore electron density is affected by sunlight, and during the night, the electron density is much less. Obviously, you can expect that ranges will get affected by night. Seasonal activity. Tilt of the Earth's axis and rotation causes sporadic electron activity during summers. And also, there is something called 11-year cycles, where there is an enhanced ultraviolet and X-ray radiation from the sun. So, there is increased absorption in D and E layer affecting communication. Now, here I've tried to show two graphs, just trying to show the electron density by day and night, just to give you an idea how much it varies between day and night. Let me quickly summarize attenuation of EM waves. Electron density affects attenuation. That means higher the electron density, of course, there is an energy loss is there. Greater the density, larger is the attenuation. Therefore, that's another important aspect we need to understand. Penetration depth. The deeper the layer of penetration, greater is the attenuation, because it has traveled and it is reaching atmosphere of higher electron density. Frequency, lower is the frequency, higher is the attenuation. This is only applicable for sky waves, space waves, as I want you to know. It is different from what we learnt earlier. I want you to notice that. This is a very simple summary of what we learned. At some frequency range, these EM waves are able to hop over several times, provided it has got adequate energy, and it's able to reach much farther distances. This is called multi-hop reflection. Reflection. Earlier days, we used to have a nav aid called Omega navigation system, which would work in very low frequency range, and there were simply just about 6 aerials all over the world which covered the entire world. So it was able to give much longer ranges, almost 4,000, 5,000 nautical miles, because of such propagation properties. That's what I want you to understand. There's another phenomena which I want to cover, which is called the duck propagation. What happens when atmosphere is moist? Then that it affects in such a way that it's able to bend these waves in much longer for much long at much lower levels, and therefore you are able to reach longer distances. Now it is a little bit very clear. That means it doesn't have to reach the top layers of the atmosphere. If it is, it gets bent and reflected at a much lower level, and at some times you are able to reach over long distances. This is called duck propagation. The basic conditions that are required are warm, dry air blowing over the cool sea subsidence and pronounced radiation cooling. Of course, there's more to be covered, but just to keep the time restricted, I have restricted the content at this point, and you all can go through the theory and learn further. And if there is a need, I will cover some more propagation properties in the next lesson. I hope you found this lesson useful, and please follow all our lessons in our YouTube channel and on our website, and please feel free to pass it on to anybody who could benefit from this. And of course, your critical comments are any day welcome on this mail ID. Thank you.